project presentations are starting, I guess, next class. I guess people who were actually celebrating Thanksgiving did not get to have the next Monday slots, so they got this Wednesday slots. Talking about that, I am perfectly alright with having this Wednesday's class be held next Wednesday. Okay, so next Wednesday is basically reading day. Okay, so we can cancel this Wednesday's class, hold the meeting next Wednesday, and then the Wednesday guys will be next Wednesday, and this Wednesday's guys will be next Monday. It's fine with me. I mean, to the extent if people are not ready, there is no point in, I'm assuming, based on what's going on and who actually wound up signing up for the first day and who wound up signing up for the last day. But then, I'm okay with it, but it is the reading day, and if any of you would rather, we have exams or something and they need to study for that, then, I can't do that. So, is there anyone with possible objections for doing that? Okay. So, in that case, then essentially, and right after this class, if you could not bring yourself to say it in front of everybody and get killed, because, you'd be the reason why, just send a mail to me right after the class, and I'll wait for an hour or two after the class and then confirm that this is what we're going to do. And then I will try to hold, because it's a reading day, I'm assuming this will be available for the same time next Wednesday too. And so, basically it will still be the first set of talks and the second set of talks. And the first set of talks will be held next Monday, second set of talks will be held next Wednesday. Okay?
Will you send us an email telling us which one actually happens?
Yeah, that's what I'm saying. I will confirm that there is, unless I hear from somebody from the class, I won't name names. I understand that people could have plans, regarding studying for the exam or something. So if anybody has problems with that, then I can't do it legally. Okay, but if there is nobody, and if you have problems, then you should let me know in an hour, after the class, and then before this evening, I'll send you a mail confirm. Okay. Then in that case, and the way these things will work, I would actually prefer to get your the slides up on the web page before, so that I can actually give you some comments as to whether or not it's supposed to make sense to other people too. And so you can send me an email first of all, just the slides. If you don't want to put it up on the web page, you can send me an email and then I can look at them, and then once the things are ready, then they should be on the web page. Okay. And also and remember that the AAAI paper reviews should be there on that page. I don't know how many people actually have already done that. Okay, let's see. Yeah, so I know a couple of people have started writing. There is one. This is not to kind of. Also, there's two. That much I know, but the rest of you haven't done it yet. Okay. Again, my point is not to put those two people who completed on the spot, but to actually get the other people who didn't complete on the spot, and then make sure that you write it. Okay. So if that's the case, then like I said, I will confirm, but after that. The class about whether the Monday, Wednesday thing is to happen. So I was going to actually say that this is going to be a general discussion class. Okay. So if you I'm not really sure how many of you have things that you brought to discuss. So since I wasn't sure, that rather than, I also prepared to talk about temporal probabilistic models, which is one topic that I didn't particularly discuss in this semester. So are there any things that people wanted to talk about regarding the topics that we have covered, or am I doing this? Yeah?
I had a brief question on the classical planning part.
Mm-hmm.
So when we were talking about writing a domain description, it seemed like we were discussing two different notions of state at the same time. One would be a state of the domain, and the other would be a state of the graph, or within the particular algorithm being explored. For example,
Oh, no, you're talking about, so you're talking about are you possibly talking about the world state versus search states?
Yes.
Distinction?
Yes.
Yeah, but that's just normal for any, when we talked about A* search, we knew, for example, that the world state for like an 8 puzzle problem is exactly what the 8 puzzle problem's configuration is. A search state, on the other hand, might correspond. Two search states might have the same world state but have different parents, so you came to them differently. So
the question that I had is, within that planning community, are domain descriptions, for example, that might be submitted to some planning competition, are they informed by the model used by the particular algorithm of their planner?
no. So the question, I assume, is, so in classical planning, in planning in general, there was a tendency to separate domain physics from know-how. Okay, the know-how basically means, a procedure for actually solving the problem. Okay, all the domains that you have looked at till now, the PDDL domains you have looked at or we talked about in the class, they're all just pure domain physics. Okay, they don't take into account any specific way. They're not telling a specific way of solving the problem. And when you start getting into a specific way of solving the problem, then you have to get into, is that procedural knowledge tailored to a particular planner or not? Okay, there is an entire topic called knowledge-based planning, which again I did not discuss here. Which basically is aimed at adding on top of the domain physics additional know-how information. You may have heard of hierarchical task network, or you may have heard of TL plan control axioms. These are all additional information that you are telling the planner, saying, if you, for example, the HTN planner might be saying that you always try to go from here to San Francisco either by flight or by train or by, either by flight or by train, that's it. So that means even though it's going part way by, hitchhiking, then part way by bicycling, etc., will still get you to San Francisco. You don't allow those to be, valid solutions. And that sort of tells the planner how to solve the problem. Okay, so knowledge-based planning, so HTM planning domains will be giving that kind of information that you're talking about, which is domain-specific information, procedural information about how to solve the problem. And when it gives that, the question, when you're talking about knowledge-based planning, there are, in fact, that becomes an interesting issue. Is this just additional knowledge about how to solve the problem, or is it, in fact, talking about very specific planner's search space? So, one type of knowledge-based planning might actually give you control rules saying, when you have the following open conditions to be resolved, and the following links are unsafe, then pick this particular resolution. Okay, now when I said that, you can clearly see that this kind of a rule can't be useful particularly for a state space planner. It's meant for a partial order planner. Okay, but that's a kind of control knowledge that somebody who knows the planner and the domain can write. And there is also types of control knowledge like HTNs are basically the temporal logic axioms, which an expert who doesn't quite know the underlying procedures used by your planner might be able to provide. Now when they provide it, whether or not a particular planner can exploit them well depends again upon the planner. So for example, a temporal logic axiom which says, for example, whenever you have the following sequence of states, it's not a good thing. So then that kind of an axiom is very easy to use for a forward search planner. Not as easy to use for a partial order planner. Okay, similarly, HTN planning, the original kind of HTN planning, was actually very easy to use for a partial order planner and not as well suited for forward search planners. And there are variations of HTN planning know-how which have been, such as, for example, you may have heard of, we didn't talk about it here, but there is a planner called SHARP, which many people use for their domains. And there essentially you almost remove the distinction between which part is know-how, which part is domain physics. So SHARP would be a higher level language for writing a little planner for solving problems in the domain. And it contains both the knowledge, both the declarative knowledge, and also when you have the following choices, take this first, and then this, and then this. Okay, and that's a state space type. Okay, and yeah, so we did not go into knowledge-based planning. In fact, the closest that we might come to is when Randy is doing one of the projects, who is going to talk about if you have a hierarchicalization of a domain, and then you start saying there are high-level tasks which are then split into lower-level tasks, and finally you have the primitive tasks in the bottom. And if I give you the hierarchicalization, then can you automatically compute the effects and preconditions of these intermediate tasks? Normally, even those are given by the users, for the domain writers in HTN planning. But if I just give you the hierarchicalization, can you compute bounds on the effects and preconditions? That's something that he would be discussing, but we didn't discuss the background topic on knowledge-based planning. If you look at my 574 notes, there is there are lectures on that. Any other questions? Okay, so I was not too off the possibility that we will have to stare at each other, and so I came up with some topic to discuss, because it's so much easier to just listen, right, rather than actually think, and come up with questions. So this is the topic that it's relevant, and in fact it also flows within what we've been discussing, which is last time we ended with with basically relational models, probabilistic relational models, and we talked about templated probabilistic models. Okay, so here we'll talk about temporal probabilistic models, which is basically Bayes networks generalized to handle temporal processes. So if you have a temporal process, then for example you have a set of variables xi, so x, but then they are indexed by the time point. So x at time point I, x at time point I plus 1, I plus 2, etc. And so you may have a process, and you have the process then also provides observations, and so xi and oi are the observations, and you want to talk about how would you model it as a Bayes network. And in fact, one of the interesting things we'll see is when you model it as a Bayes network, you will get a little template called dynamic Bayes network, where you essentially say how xi becomes xi plus 1. And then once I give you that one slice temporal model, then if I need to start from x0 to x10, then I just say x0 to x1, and then copy x1 to x2, x2 to x3, and so on. So I just basically unroll the network. I'll show you examples in a minute. Okay. So in this sense, a dynamic Bayes network, which is what we'll talk about as the background for temporal probabilistic models, as the representation for temporal probabilistic models, it's sort of like probabilistic relational models. It also provides you a template for what to do to go from I to I plus 1, and then you just repeat, you copy it over multiple times to reason over a longer horizon. Okay, so that's actually a proximal connection from the last class discussion to this class discussion. But these are also actually quite interesting in their own accord. So we'll just talk about some of the issues involved in dealing with temporal probabilistic models. Okay, so it's a process. Temporal process is an evolution of a system state over time. So you have a state at xi plus 1, xi plus 2. So we are assuming basically discrete time, I plus 1, I plus 2 instead of absolute metric time. Okay, for now at least. And then often the system state is hidden. So in fact, what you really get is not the state itself, but an observation from the state. And the more interesting part is given the observations, can you reconstruct the states and do some interesting inference about what states you may have passed through. Okay, and in some sense, the questions that we'll be discussing here are sort of easier than POMDP. In fact, if you have, for example, hidden system state, right, and then so you are only looking at the observations. So you're looking at the observations coming from somebody else's POMDP policy. Okay, and then you're trying to compute their states that they have gone through. Whereas in POMDP, you actually have control over what happens next. And with that control, you need to then maximize your utility and so on. Okay, and if the state is completely observable, then what you are seeing is a fully observable plan by somebody. Somebody is they went from this state to this state to this state to this state, and you are watching that and you are trying to figure out what's going to happen next. Okay, so that would be a simple Markov chain, and the version that I talked about is also sometimes called the hidden Markov model. Okay, but in general, a more general representation for all of these, you'll see is something called a dynamic Bayes net, where essentially you provide the Bayes network on xi and xi plus 1. That means the state and observation variables at time point I, and how they relate to those at time point I plus 1. Okay, and once we give that, then you assume that that template is repeated as you go from I plus 1 to I plus 2. Okay, so that's of course a relation to planning. We talked about state estimation. In fact, these are particularly interesting in terms of, as you see the process evolving in front of you, you want to estimate based on just the observations you have seen till now, what is the most likely state the system currently is in. And sometimes, in fact, we'll see also that you may not only want to know what the current state is, but you may also want to know what is the sequence of states the system has gone through to get here. Okay, so these are called state estimation problems as against planning problems, where you essentially have control over what states will occur, because you are also picking actions. Here somebody else is picking actions, you're only estimating the state based on partial information. Okay, we looked at this in the context of non-deterministic scenarios, but it wasn't very interesting there, because in non-deterministic scenarios in particular, if it is fully observable, there is nothing to estimate. Right? And if it is partially observable, then the question of course is, the observation model itself is deterministic in non-deterministic scenarios, in the sense that either this observation will happen from the state or it won't happen from the state. Saying it may happen, I don't know how to use that information. Whereas once you have probabilistic models, you could say the probability that observation O comes, given that the internal state is S, doesn't have to be just 0 and 1, but it can be any number between 0 and 1. So you can talk about noisy observations, some of which, given this state, this observation is more likely, 0.7 likely. This one is even more likely, 0.71 likely. Okay. So it provides you a finer grained connection between the observations and the state, hidden state. Because of which state estimation in probabilistic models is actually quite much more interesting. I mentioned this exact thing, many classes back when I showed you that picture before. I said, in fact, we'll see that state estimation is in itself a non-trivial problem once you have stochastic planning. Okay, and I think, in fact, I showed you that particle filtering example where the robot localizes itself. This is that class, actually. I'm going to get you back to that and explain to you what are the actual Bayes network inference that you're doing, and what are the types of inference that you need to do, and what are the types of algorithms that you want for doing that inference. Okay, that's what we'll try to do depending on the time. Okay. Okay, so the basic idea, our representation is that x sub t is the set of unobservable state variables at time t. Okay, and E sub t is the observable evidence variables, or what are the observations at time t. Okay, now of course, if in fact you believe that xt is completely observable, then Et is just xt.
This
right?
is from the frame of reference of the agent himself.
This is from the frame of reference from the observer. From the observer. Okay? Or actually, in fact, the interesting thing is the observer will never know what x really is, but they only have evidence about what the x would be. We'll see an example in a minute. Okay, so the assumption then, and then we'll use this notation oftentimes. Again, this is from the chapter 16, I believe, temporal probabilistic models in the textbook, Russell and Arvin. Okay, so we'll use x a colon b to mean the sequence xa plus 1, etc., xb. Okay, and then we are assuming, of course, discrete time. Okay, so these are all basically when you are looking at somebody else's. So just like we had Markov decision processes until now, POM-DPs and MDPs. Now you have just Markov process, because there is no decision for you to make. You don't get to change the world. You only get to guess where the world is, because it's somebody else's plan. You are just an observer. Okay, and that happens oftentimes. Okay, so in fact, so basically you are talking about Markov chains. If it's a fully observable case, the MDP becomes a Markov chain. And it's a partially observable case, POM-DP becomes an HMM, hidden Markov model. Okay, now the part about Markov really is, Markov assumption only says that the state at time t depends only on some bounded subset of the states from 0 to t minus 1. Okay, and the first order Markov process says xt depends only on xt minus 1. Okay, second order means xt only depends on xt minus 1 and xt minus 2. Third order means xt minus 1, xt minus 2, xt minus 3. Okay, and if it depends on all of them, if it's not bounded, then it won't be bounded, because as you increase time t, the number of states that you have come to keeps increasing, so it would not be bounded anymore. Okay, so a kth order process can be talked about as being just dependent on the k previous states. Okay, so here is your first order, here is your second order, and so on. Now, this is about the state Markov assumption. There is an equivalent assumption we make for the sensors. Not equivalent, similar assumption we make for the sensors. We assume that the sensors are dependent only on the current state, nothing else. The observation you get right now depends only on today's state, not yesterday's state. Okay, to the extent yesterday's state has something to do with this observation, it should be reflected in today's state. That's the basic idea. Okay, so sensor Markov assumption is Et given x0 to t and E0 to t minus 1, E is nothing but Et given xt. Now in fact the Markov assumptions, all of these Markov assumptions can be thought of essentially as conditional independence assumptions. Right? Remember, Bayes networks are all about conditional independences. So we are saying probability of the distribution of xt given x0 to t minus 1 is just xt given xt minus 1, because the rest don't matter. So it's a great conditional independence assertion. And when you have a conditional independence, that basically means the underlying Bayes net doesn't need links from anything that is independent of, that it's independent of. Okay? So once I have a link from t minus 2 to t minus 1, I don't need a link from t minus 3 to t minus 1, because anyway, it's not that t minus 3 doesn't affect t minus 1, it is only affecting t minus 1 through t minus 2. Whereas here, t minus 2 affects t both directly and through t minus 1. Okay, so this, you can think of these as processes, simple process diagrams, or you can think of them as actually Bayes networks, which they are. And by looking at these as Bayes networks, you now actually see that here all I need is a CPT for xt minus 1 given xt minus 2. And then I need a CPT for xt given xt minus 1. Whereas here I need a CPT for xt given xt minus 1 and xt minus 2. So it's a much bigger CPT now. You see what I'm saying? So I need more parameters to be specified. More edges means more parameters to be specified, which also means more parameters to be learned if nobody is specifying it for you. Okay. So that's the thing about looking at this as, and then finally for the sensor Markov assumption, if there is evidences from each thing. So right now I'm saying an evidence at t doesn't depend on anything other than state at t. So if I were to write evidence variables into this network, then essentially I'll just have this showing OT minus 2. Here OT minus 1. Here, ET minus 2, ET minus 1, ET, and so on. Okay? Now, finally, the question is, the way I wrote this up until now, these are only Markov assumptions. Nothing, this hasn't yet gotten us to the templated issue. The template issue is, right now, if this is my network, I need a CPT here, I need a CPT here, I need a CPT here, I need a CPT here. Stationarity assumption says all those CPTs are the same. Do you understand what I'm saying? So, if the probability that xt minus, suppose for a minute they're all true-false variables, then the probability that xt is true given xt minus 1 is true is the same as the probability that xt plus 2 is true given xt plus 1 is true. So I don't need to give a different CPT. So I'm assuming that the underlying process is stationary, and so the probability of xt's dependence on xt minus 1 is the same as xt plus 1's dependence on xt. The moment you make that stationarity assumption, that's not a conditional independence assumption. That is an assumption about replicated structure. Okay, so once I do that, then I can specify this network by just giving one CPT, and I can specify this network by just giving this, these three. So to specify a first order Markov chain, I only need to show you xt minus 1, xt minus, I need to show you xt minus 1 and how xt minus 1 affects xt. And also the CPT for, the prior for xt minus 1. Okay? And then similarly for the second order one, I need to show you a network involving 3 nodes, because that gets unrolled. Okay? With the stationarity assumption, essentially, I give you just the template from how to go from, especially for the first order case, t minus 1 to t, and then what the probabilities are, and then you can then expand it from 0 to 18, for example, if you need. Okay? And so stationarity assumption over time is sort of like relational assumptions over objects. You're saying all time is similar. That means the way xt depends on xt minus 1 is the same as the way xt plus 1 depends on xt. That's an assumption on the process. It's not always the case. It's actually possible. It's actually possible that the process is non-stationary. In which case, really, for example, it could be also piecewise stationary. There may be a process which is stationary for the daytime and then a separate stationary process for the night time. Do you see what I'm saying? And so you will have to say that it's piecewise stationary. Okay, so if the whole thing is not stationary, you can split it into pieces and say it's piecewise stationary over these pieces. That will again reduce the number of parameters you need to learn. Similarly, in the relational assumption, we assumed that all objects of a particular type, that's all courses, are the same. And so, in fact, last time we were talking about authors, papers, reviewers. Right? We assumed all authors are same, all reviewers are same. Okay? And so, the way a particular author influences the quality of their paper is the same as another particular author influences the quality of their paper. If you do not believe that somehow if you believe that there is a difference between Western European authors and Eastern Asian authors, then you split it into two separate equivalence classes and then say those equivalence classes are again similar. And the name of the game here is you need to assume so that you can reduce the number of parameters that you need to specify. Okay? In this case, you assume stationarity, and that will reduce the number of parameters. Okay, so here is an example, a simple example. This one is the rain process. So in fact, the textbook talks about this. So you are, let's say, you are sitting in a room with no windows, nothing, and then all you see is you never go home. You just stay at home, stay in this room. Okay, and your co-workers come in and go back home, come in and go back home. And some days they come in with their umbrella, some days they don't come in with their umbrella. Based on whether they are coming with their umbrellas or not. All you can observe is whether they came in with an umbrella or not. Based on whether you saw them coming with an umbrella or not, you're trying to guess whether it was raining outside that day. So the state that you're interested in is rain for the day t. Okay? So then rain t minus 1, rain t plus 1, etc. Now, rain itself is a stationary process. If it was raining yesterday, it's a little more likely that it will rain today. And if it was not raining yesterday, it's more likely that it won't rain today. But it's only likely. It's not that if it's not raining yesterday, it won't rain today. It's not a deterministic connection, it's a probabilistic connection. Okay, so the way rain would go, rain t minus 1 influences rain t, is if t minus 1 is true, that means if previously it was raining, it will rain today also with 0.7 probability. If previous day it was not raining, it will rain today only with 0.3 probability. Suppose that is the actual process. But then what you actually see is the umbrellas. Now the umbrellas also are noisy. You only need to see people actually when it's raining to realize that some people actually like rain. They want to walk in it. Okay, they don't bring in umbrellas. Okay, so your co-worker may be one of those kinds of people who sometimes is not directly correlated with whether or not it's raining. It's not 100% correlated. So if it is raining, you are much more likely to see your co-worker bringing the umbrella than not. And even if it's not raining, you also have seen, a large number of people who don't want to get overly tanned, and so they essentially, hold an umbrella so that their complexion could be preserved, right? And so in which case, even when it's not raining, there's a small probability, 0.2, that somebody would be carrying an umbrella. Suppose this is my model. Okay, then in essence, the guy in the room is seeing umbrellas, and based on that, he's trying to guess whether or not it was raining on a particular day. Okay, and obviously they don't have access to this information. They only have access to this information. They don't have access to, they have access to this. In the sense they can read a textbook to realize, even if you don't get to go out, you can read a textbook to realize that if it's raining one day, it's more likely to rain next day. If it's not raining one day, it's less likely to rain next day. The theory of rain they know. It's the practice of rain that they don't know because they have no windows and they don't get to go out. And so based on these observations, they are trying to reconstruct what really is happening outside. That's your essentially temporal process. That's the kind of reasoning you need to do with the temporal process. Okay, now this one, in this particular case, is this a first order or second order or nth order Markov process? First order, because rain t minus 1 only depends on rain t. Okay, now sometimes first order Markovian assumption doesn't hold. I already told you if the stationary doesn't hold, you might make it piecewise stationary. Okay, and if the Markovian assumption doesn't hold, if the first order Markovian assumption doesn't hold, you can do a couple of things. You can increase the order of the Markov process and make it second order, or you can augment the state. In fact, if it is more than, first order Markov, that means there is some aspect of the previous two states previous state which is not being carried through. And so you need to look at that state also to decide how it affects the current state. So one way of doing that is to augment the state description with more variables. State description with more variables. Okay, and so if you increase the state size with additional variables, additional state variables, sometimes you would be first order Markovian in this increased size of state. Those are the two ways you can make something that's not first order Markovian into a first order Markovian. By the way, when somebody says Markovian, normally they just mean first order Markovian. Okay.
Is there a point at which increasing the order is roughly equivalent in terms of the complexity you get of the system as opposed to augmenting state?
I don't know that there are any theoretical results on that. But sometimes one of these might be a better thing to do than this. But I don't know of any obvious results as to which one would you do when. Okay, so that's your example. Now, this is a simple kind of an example. This is already a dynamic Bayes network, right? It's a dynamic Bayes network in sense. In fact, all I need to really specify to you is this part. Okay, in fact, what I really need to specify, it turns out, for the dynamic Bayes network, for that case, is rain 0, okay, and how it affects rain 1, which then affects umbrella 1. Okay, so I need a CPT here, which tells me when is umbrella true, what's the probability of being umbrella true given rain is true versus false. I need a CPT here, which basically says what's the probability that rain 1 is true given rain 0 is true, and what's the probability rain 1 is true given rain 0 is false. And then a prior probability here. Originally, when the universe started, was it a rainy day or not? Okay, because after that, everybody else's distribution is determined by their previous case distribution. Okay, if I do this, then to get rain 2, I just take this part, copy it over here. Okay, and that's basically a dynamic Bayes network. So that's what I just wrote here: rain 0, rain 1, umbrella 1. Okay, and you could also have more complicated dynamic Bayes networks. So for example, here, a battery level, velocity and position, and then battery level in the next time point, velocity in the next time point, position at the next time point, and then the position gives you an observation about the position, and the battery gives you an observation about the strength of the battery through the battery meter. Okay. One other interesting thing actually is, although it's not shown here, in general there could be links, not just these links are called diachronic links. That means this shows how 0 is affecting 1 or I is affecting I plus 1. Okay, and notice interestingly that this wasn't obvious here. Here is because there's only one state variable. You have here three state variables. 3 state variables and 2 observation variables, right? And notice that the state variable position x1 depends on both the velocity and the position in the previous level. And battery depends on both, battery only depends on the battery last time. Velocity depends on both the battery and the velocity previous time. That's what I'm saying right now. This is my theory of how the world is working. Okay, now since there are no connections within the variables at a particular time point, that means those variables, state variables, are all independent. But that's not necessary. Sometimes I could have, state variables themselves being dependent on each other. Okay, in which case I could wind up having connections here too. And those would be called synchronic arcs. That means it's essentially if you're thinking in terms of axioms, these are interstate dependencies, and those would be intrastate dependencies. Okay, and so a dynamic Bayes network essentially is is showing both how you evolve from one time point to the next time point, and it can also show how the values in a particular time point are correlated with each other. If there are no connections, that means they are not correlated. They are completely independently chosen. Right? Okay. One other thing I should go forward and come back in a minute is that from our point of view, actually, the dynamic Bayes networks were actually, we talked about it very briefly in passing when we talked about stochastic planning. Because if you are representing a stochastic action, okay, you need to talk about what is true, what needs to be true before the action, and what would be the values of the state variables after the action. Okay, and one way you can represent a stochastic action is a two-time Bayes network, 2TBN. And that's a dynamic Bayes network. Okay, the only difference, of course, is when we looked at this the last time around, we were interested in actually choosing the actions we want. We can choose which action we are going to do. Now we are just, outsiders. We are just watching the world, progress. Right? Okay. So this was the 2TBN representation, and remember we actually mentioned that time that IPPC doesn't use that. IPPC instead of using this 2TBN representation, it uses more like this strips representation, where it essentially says under these conditions, this is the total set of changes to the state with the different probabilities. And this is for these conditions, here is this mutually exclusive and exhaustive set of changes, and here is a different one. Okay, but this is actually a more general way of representing, the actions. This can be compiled down to this. Okay, and again you'll notice that in this case the variables RHC is now going to be dependent on log and RHC in the previous level, and CR depends on CR, RHC and log in the previous level. That means pre-action and post-action variable values. Okay, so that's again just to remind you that the dynamic Bayes networks were also useful for representing the stochastic actions. Okay, so now let's go back to the previous discussion. Okay, so so we have this, we also can talk about actions, and this is a more general dynamic Bayes network. And as I said, you can also have synchronic and diachronic arcs. Okay. Now, it's a Bayes network ultimately. So what's interesting, why should we study dynamic Bayes networks differently from Bayes networks? Okay, the interesting point is, in a general Bayes network, you can give a subset of variables as the evidence and ask posterior on another subset of variables. Right? In a Bayes network, you give some variables are observed, and you want to know posteriors on the query variables. Okay. Now, what's interesting about dynamic Bayes networks is not all subsets of query and evidence variables are created equal. For example, in this case, I would never give evidence on the state because the state is unobservable. So all the evidence in the dynamic Bayes networks would be about these evidence nodes. Only those will ever be seen. In a generic Bayes network, any particular value could be seen. But in dynamic Bayes networks, only the observation variables would be seen. And your query will always be about states. Because what you're interested in seeing is, what is the state based on the observation? You are barely likely to ask, what was the observation? What's the observation going to be day after tomorrow? You're much more likely to ask, what's the state going to be day after tomorrow? Okay, so essentially it's worth thinking of inference tasks that are particularly interesting to dynamic Bayes networks. Do you understand what I'm saying? So these are also inference tasks for normal Bayes networks. It's just that they have special significance for dynamic Bayes networks because you have a difference between observation variables and the state variables, and you also, state is hidden and you are always trying to guess the state. Okay, and what's another thing that's interesting is that you have a repeating process. State, observation, state, observation, state, observation, state, observation. Okay, and you only get the observations and you're trying to guess what the states are. So, what kind of questions would you be interested in asking? The first question is, given all the observations, where the heck am I? Is it raining outside today or not? Given all the observations I have seen, is it raining outside today or not? Okay, that is filtering. That's basically also called state estimation problem. Okay, now here is the interesting thing. Although the underlying process is Markovian, on the states, what you think is the state right now depends not just on today's evidence, but also on all the evidence you got until now. Do you understand that? Okay, so if I wanted to know what the state is today, and you came and said, I'll give you previous state information. How many states do you want to know to guess what the state is today? I'll tell you, just give me yesterday's state. And if you come and ask me, I can give you the evidence of all the previous evidences. How many evidences do you want to know? I'll say, give me all of them. Because I need all the evidence. Okay? And this is sort of like POMDPs too. Remember, essentially in POMDPs, you had to keep track of all the evidence to figure out where your current state is. Okay? So, in filtering, what you're interested in doing is, given all the evidence from 1 to t, what is the current state? What is the distribution over the current state? That's the state estimation problem. That's like the most important problem in temporal Bayes networks. Okay? And we'll talk about how to do this in a minute. But there are other relevant ones. One other one is prediction. I don't really care about what's today. I want to know what is it going to be 7 days from today. Based on all the evidence I got till now, I want to predict what's going to happen on the exam day. That's a prediction task. Okay, the interesting thing between filtering and prediction is, in essence, you can think of prediction as figuring out where you are, for which you have evidence from 1 to t, you figure out where you are. And then from where you are to 7 days from today, I'm no longer going to have any evidence because I'm right now here. I haven't yet gotten the evidence for the next 7 days. So the best I can do is, if I know the state right now, I just push that state distribution through the state transition function. to get the state distribution 7 days from now. Now you might say, what's the difference between that and filtering? Because in filtering too, I can be pushing the evidence, pushing the initial state distribution through the transition function. I know the initial state distribution, which is the prior, and I through this transition function. Yes, except having pushed it to range 1, and I get, let's say, a distribution of range 1, I then can improve the distribution because I have observation. So using the Bayes rule, I can then improve the observation. Okay, we'll see it in a minute, but in fact, if you must look at it, here is an example. So here is range 0. Let's say in the beginning, rain can occur or not occur with 0.5 probability. Okay, then first day, rain is going to occur based on just the transition matrix. The probability that rain will occur on the first day will again be 0.5. But then if I showed you that umbrella was seen on first day, then I will change this to 0.818 and 0.18. Which is what I would then push through the transition matrix here to get the second day's rain, which then, made consistent with the observation, becomes more informative. Notice, of course, that this is what I expect, and this is how I change my expectation based on the observation. And the observation might reduce my expectation as well as increase my observation. It just basically changes the distribution. And so the difference between filtering and prediction is in the filtering task, you do this at every level. Predict one level, make it consistent with the observation at that level. Predict to one more level, make it consistent with the observation there. And you take that to the third level, make it again consistent with the third level. And then when you do it in the last level, where you currently are, you will get your best shot at what the current state distribution is. In the prediction task, you not only now know, I know what my current state distribution is, I want to know what it will be 7 days from now without being given any evidence. So all I can do is just transition it through the transition matrix. And because it's a noisy transition matrix, uncertainty just keeps increasing. Okay, without observation, essentially the entropy keeps increasing on the distribution. Without observation, in essence, as you go far into the future, if it is at all noisy distribution, as you go far into the future, everything will become equally likely. And it's the observations which are kind of getting you back on track. Okay, so that's the prediction problem. Okay, the smoothing problem is interesting actually. You are saying, what is the state 10 days back, given that I know where I am right now? Okay, you almost would wonder who the heck will ask it, but if you think about it, that's what we are always doing. I mean, I think I mentioned this in the class a couple of classes back, that, in some dark night, you're driving and you heard a dull thud and you thought you went over some sort of a rock, and then you came home and then you found a large amount of blood on your car. Then you changed as to your expectation as to what happened. You didn't go over a rock. There is no reason for rock to bleed, but you must have gone over some living thing. So you changed what the hidden state previously based on the observation from the current state. Do you see what I'm saying? Okay, that's smoothing. Okay, if you smooth, you have a much better feel for what really happened. Okay, so what's interesting, of course, is this one is filtering based on the fact that now I know where I am. I can actually tell you whether it was still 0.5 on the first day or not. That's smoothing. Okay. Again, notice that these are none of these are. This is just a given, probability posterior on some query variables, even some evidence variables. They are all considered just normal Bayesian queries. It's just that we subdivide them into subclasses because, based on whether you only ask if the query variable is only the current state variable, the query variable is a future state variable, if the query variable is a past state variable. Okay, and then finally, one other relevant thing is the most likely explanation. which basically says if I am in T and I got E1 to ET, okay, these are all the evidences. What must have been the exact set of states that have gotten me here? What's the most likely set of states, sequence of states that got me here? I'm not interested in finding out what is the most likely state on the 7th day. Is it raining or not raining? I want to know, give me the full sequence correct. Now that's actually less interesting for the rainy day example. And what's interesting here is that all these cases, notice, they're all distribution over a single variable. Posterior over a single variable given some evidence. This one is about posterior, it's talking about the joint distribution over x1 to xt given the evidence. And you want to know the mode of that distribution, which is the most likely value for the joint distribution of x1 to xt. Where do you need this? When I'm speaking. Okay? You could have sworn that the last word I said is a dog, let's say. Okay? But then I have my accent and you have your, flawed hearing, and we're trying to make sense of it. You don't really care what is the second word Rav said. You want to know what's the full sentence Rav said. And oftentimes the most likely second word I said might be very different from what the second word would be in the most likely sentence I said. Do you understand what I'm saying? Because I may have misspoken, and what I really want to know, or you may have misheard on that one word, but the entire sentence, this is the much more likely sentence Rav spoke than this one. Even though the second word in this sentence is less likely by itself than the second word in this sentence. Okay, and so this is actually used in speech recognition. Speech recognition is a classic case of I have a hidden state. I'm trying to enunciate some phonemes. Okay, but I am from a culture where certain phonemes are more used than others. You are from certain cultures where you can hear some phonemes and not others. And you're trying to figure out what I'm saying based on what I enunciated. And you don't really care whether Rav said, phoneme 75. You want to know what did he overall say. Okay? And so that's joint distribution being maximized. Does anybody know, so the most likely explanation, have any of you heard of Viterbi decoding? Yeah. Do you know why Viterbi is famous? For, of course, Viterbi decoding. But why is he famous now? You guys don't need jobs, I guess. Qualcomm. Okay. Viterbi started also Qualcomm. Okay. And USC School of Engineering is called Viterbi School of Engineering because he used to be like a poor professor like me, but then he started Qualcomm. So he bought the department. And so clearly he gets to teach whatever he wants. But that's a different story. So the interesting thing is Viterbi decoding is a particular kind of inference on dynamic Bayes networks. He has a more efficient way to do this particular kind of inference than you would care about, than you would have done it if you just did it from first principles. Because all you really need is the most likely one. You don't really need the full joint and find the mode. If I can compute just the mode for the full joint, then you are happy. And Viterbi decoding exactly does that. Okay? So those are the kinds of inference tasks that are of interest in dynamic Bayes inference. And let's look at a little about filtering. Okay? And I mean, see, basically, you want to know how to do all of these, but I'll tell you at least how to do one of them. And the textbook has more information on the rest. Okay? Yes?
Suppose that you have an agent operating in some domain. So you can do prediction to evaluate what the likely consequence of the plan will be.
Mm-hmm.
Suppose he goes about executing the plan and finds out that something went wrong, something doesn't line up with his prediction. Then he would do diagnosis. In that case, would that be identical to the smoothing problem? Finding out actually what state he was in, really.
That's sort of like smoothing problem. Yes, based on the evidences you got, you're trying to figure out where you were before some extent. Okay, but smoothing really is the interesting thing, and this will not happen in logic in essence. Okay, but it will happen because in some sense probabilistic logic is diffusible. Okay, and so by knowing more about where you are, you know more about where you were, essentially. Okay. Okay, so we'll talk about what kind of algorithms. So we first of all looked at what are the kinds of problems DBNs will do. These are all normal Bayes network problems, except these have special names for DBNs because these are much more interesting for them. Okay, any subset, you know, for Bayes network, P of x given y, where x is any subset of variables in the network, y is any subset of variables in the network. That's a Bayes network query. And that subsumes all of these, except these are all special cases and with names. Okay. Okay. So when you're doing inference for filtering, let's say, the simplest thing we'll do again is, because as I said, dynamic Bayes networks are templated networks. Okay. So suppose I have lived for 5 days, and I have seen umbrellas for 5 days, and I want to figure out, is it raining that day on the 5th day? Or I want to figure out, will it rain on the 8th day? Okay, one way I can do it is I can say this is just predicate logic, and here is my propositional logic version. Okay, this is template. I unroll the template all the way to 5, Okay, so now I have a simple Bayes network. So everything you ever did with simple Bayes network can be done on this. As I said, filtering is just a special class of inference problems on Bayes network, so you can use any Bayes network algorithm to solve that problem. You can do smoothing on this, you can do everything, every kind of inference. Okay, so unrolling is always the last resort, and that's what I showed you in the PRMs too. You can always unroll the underlying PRM. Okay, expand the underlying PRM, you'll get a Bayes network and just do Bayes network inference. And I said, the trick is to actually do less than that. And in fact, that's what we'll see today. Okay, so how can you do less than that in this case? Okay, can do much better if we exploit the repetitive structure. There's a lot of structure in this, and you're just repeating it into a big assembly language program. Okay, where assembly language for us is Bayes networks. Okay, so what you can do is, in fact, you can tailor algorithms that exploit the structure. You can do that both for exact and approximate cases. Remember, Bayes networks have exact inference techniques and sampling based approximate inference techniques. You can generalize both of them. Okay, if you generalize, tailor, not generalize. You can if you tailor the exact inference techniques, that's basically, you get a recursive update procedure that I'll show you in a minute. In essence, all that does is you sort of only look at Ti and Ti plus 1. And whenever you are in Ti plus 1 and you want to go to Ti plus 2, it's like think of, you have like a red carpet which is exactly 2 steps long, and you want to walk on this red carpet without ever touching the floor. So what do you do? So essentially, you need to kind of, unroll the path that you already walked on and re-roll it forward. Do you understand what I'm saying? So you basically, the Ti, so if you have so in the recursive procedure, you are in xi plus 1, unless xi minus 1, xi oi, that's where you are, and to go to xi plus 1, right, what I want to do is take this guy and take all this information up to here and put this in terms of the prior distribution for xi. Okay, and then I can basically talk about this part where I would not see oi, I see oi plus 1. Okay, so I had xi minus 1 to xi, and then using my procedure I will compute the right distribution for xi, and then that will become the prior for xi, and then I'll copy over an xi plus 1 oi plus 1 I do the same thing again. That's the recursive procedure. Okay, we'll go through the steps of it in a minute. The other interesting thing is the specialized likelihood weighting procedure, which is a sampling based approach for Bayes networks. You may remember an idea called likelihood based weighting, where you, rather than remove a sample from consideration because it's not agreeing with the evidence, you make it agree with the evidence and reduce its weight to be not 0 and 1 but any number between 0 and 1. So you start having fractional samples. And that idea can be further generalized to an idea called particle filtering. So likelihood weighting specialized to the Bayes network structure becomes the idea called particle filtering. Okay? I don't know whether I'll talk about particle filtering today, but let me at least show you the smoothing, the recursive part, because that's easy enough. And then we'll see when we'll get the calculator. Okay, so to devise a recursive state estimation algorithm in our simple scenario, what I want to do is I want to compute x of t plus 1, the distribution of t plus 1, given all the evidence from 1 to t plus 1. That's basically what this filtering problem is. So I want that to be computable as a recursive function, where the recursive function depends on the evidence at the t plus 1 and distribution of xt given e1 to t. That's exactly what I was saying. So to get this guy, I will somehow compute the posterior distribution for xi given everything, and then when I throw them all out, it becomes a prior for xi now. Okay, and then using prior for xi, I am now going to compute what is the xi plus 1's distribution. And this recursive procedure can be started in the beginning, and then you can just go step by step by step. Okay, that's what you're going to do. Okay, so it will be some function of the evidence at the t plus 1 and the full posterior distribution of xt given e1 to t. Right? That can be written. So how do I derive that? So xt plus 1 given e1 to t plus 1 can be written as xt plus 1 given e1 to t and t plus 1. There's nothing wrong with that, right? I mean, instead of taking all the evidence, I said all the evidence up to time t and the evidence at time t plus 1. Now using the chain rule, okay, I can then say, using the Bayes rule, okay, I can then say that this is nothing but probability of et plus 1 given xt plus 1 and e1 to t and xt plus 1 given e1 to t. Okay, it uses Bayes rule as well as chain rule together to do this. Okay, now at this point you have et plus 1 given xt plus 1 and e1 to t. Here you have the sensor Markovianity. Et plus 1 depends only on xt plus 1. So it's independent of the previous evidence given xt plus 1. So I can write this as probability of et plus 1 given xt plus 1. Okay, and then this one is xt plus 1 given e1 to t. Okay, so now what I want to know is what is the probability of xt plus 1 given evidence only up to t. Now that is really depends on what is xt and how xt will go to xt plus 1. So to compute this, I will essentially sum out xt. I will sum out. So basically the idea is e1 to t, given e1 to t, I will have different values of xt.